Hi everyone. In this video I'm going to show you how you can estimate composite reliability, also equivalent to McDonald's omega, using the AMOS program, and I'm going to be demonstrating this in the context of a two-factor confirmatory factor analysis. Now before we get started, I want to mention that this video presentation is designed to accompany a PowerPoint that I've put together on the topic, and the PowerPoint actually goes into a lot more detail concerning interpretation and so forth than I'm going to be covering in this video. You can access a copy of that PowerPoint by following the link that is provided underneath the video description. Also within the PowerPoint you will find links to the SPSS data file that I'm using throughout this demonstration, as well as to the two AMOS files that I will be working with. So let's go ahead and get started by considering the model that we are testing. So this model is based off of a presentation by Brown from 2006, and essentially what he was doing was testing a two-factor model with items from a measure of psychological reactions to stress or trauma. And so the proposed factors were intrusions and avoidance. And so you'll notice that the part of the factor model associated with intrusions, the intrusions factor, does not contain any correlated errors, whereas the portion of the model associated with the avoidance factor does incorporate a correlated error. So that's given by this double-headed arrow up here. Now, with Brown's presentation, he did focus on using Lisserl in running the model, and so again, we're going to be using AMOS. And what I thought I would do is show you a couple of approaches that you could take. One is the use of a phantom variable approach, and I actually demonstrated this in a previous video. I'll include a link to that underneath the video description. But I also thought I would incorporate a demonstration of an approach that I've come up with using the User Defined Estimands. And additionally, I thought I would also show you how you could generate bootstrap confidence intervals for your reliability estimates. Now, the data that we are working with is a summary matrix data. So this is just a screenshot from the SPSS data file. And you'll notice that we have our variables y1 through y8. Those are our indicators, or basically the items from the scale. And you'll notice that we have the correlations that are given, as well as the standard deviations for each of the items and the sample size. Okay, so now I've opened up the AMOS file that I've created for this demonstration using the phantom variable approach. So this is basically the first approach that's covered in the PowerPoint. And I'm going to go ahead and assume that you already know how to use AMOS to draw out the model. So I'm going to be focusing mainly on the components of this particular model. So first off, let's start off by looking at our the basic factor model. So we have avoidance right here and intrusions right here. So these are the two latent factors that are proposed to account for the variability in the individual items. So you've got intrusions that's associated with y1, y2, y3, and y4, and avoidance that's associated with y5, y6, y7, and y8. And you'll notice that we have single-headed arrows that are pointing from our factors to the indicator variables. Now you'll notice that's associated with each of our factors, I've basically fixed the variances of those factors to 1. Okay, so basically, whenever you're running SEM, you have to scale or set a measurement scale for all of your latent variables and also your error terms. So one way is to fix the variances of your latent variables to 1, or you can scale them in relation to the indicator variables by essentially choosing a reference indicator and fixing a factor loading to 1. But in this case, for this demonstration, I'm going to stick with fixing the variance of each of those latent variables to 1. Additionally, as you're looking at this, you can also see that we have from our indicator variables y1 through y4 and y5 through y8, we have single-headed arrows pointing from those indicators to another variable, and it looks like a latent variable, but basically it's a phantom variable that we are creating. It represents a composition of the total variation associated with the individual items. So it's kind of analogous to summing up items in SPSS. So you'll notice that from each, the single-headed arrows that are given, all of these have a loading of 1. Okay, so what we're doing is we are creating variables that represent a composition or a composite of the information from the indicator variables. And what we will essentially be doing when we run our analysis is we are going to generate model implied correlations between our latent factors and their respective phantom variables, and then from there derive the reliability estimate. One other thing to kind of note in this model, you'll see right here we have the correlated error between the item 7 and 8 error terms. So there's the error term that are terms for those items that are given. Okay, so once we've specified our model in this way, we're going to go over to analysis properties and click on this. And again, I haven't walked you through the importation of data, but just really quickly I'll show you. If you go under data view, this is that SPSS file that I was talking about earlier. And so going under analysis properties, you can see under estimation, really we're sticking with all the defaults. Under output, I have selected a couple of things that are important: standardized estimates right here and all implied moments. So those are going to be really important when it comes to computing the reliability estimate. You'll also see I've asked for squared multiple correlations, although that's not actually going to factor into the reliability estimate. And let's say I want to bootstrap or come up with a bootstrap confidence interval for the reliability estimate. I can go under bootstrap right here, and you can see I've already selected several things. First, I've selected perform bootstrap, bias corrected confidence interval. I set this for a 95% confidence interval. And then because I'm dealing with summary data, not the raw data, then I'm going to select this option right here. This gives me a Monte Carlo parametric bootstrap. So if I use this in conjunction with these other two options, I can get a bootstrap confidence interval around our estimate. If I was using the raw data itself, then I would not be selecting the Monte Carlo option. I would just be sticking with the perform bootstrap and bias corrected confidence intervals. I do want to mention that if you are using raw data, though, you would not be able to use the bootstrap option if you have any missing data. So that is a limitation of the program. So at any rate, we'll go ahead and close this out, and we'll click on calculate estimates right here. And you'll notice that this little warning message comes up. And the reason why this is coming up is because we have arrows that are pointing to these two variables, and basically AMOS is saying, hey, these variables look like they're endogenous variables because you have arrows pointing to them. And it's just saying that if we try to run this, you're leaving out the disturbance terms. And to tell you the truth, we can still proceed with the analysis, and everything is going to be golden. It's going to be fine. There's no problem with that. It's just that it was telling us that we're recognizing this as an outcome variable, and you don't have a disturbance term associated with it. But again, what we're doing is we're summing up the information from the items to produce that phantom variable. I will say that if you wanted to, if it disturbs you not to have a disturbance term associated with it, you can certainly add it. You can go up here to where it says add a unique variable, and we can click on this and just kind of move this around here. And we can add it just by, I'm going to go to object properties. I can name it. I'll just call this D1 and D2 right here. Now the thing about it, though, is that we need to fix the parameters here, the variance of these, to 0. So if I fix that one to 0 and I fix this one to 0, if I run this particular analysis, it's going to give me literally the same model fit and everything. So it works out exactly the same. So I'm going to go ahead and just kind of remove these. We'll stick with the previous specification, but again, if that bothers you that there are no disturbance terms in there, then you can certainly do that. So again, we're just kind of proceeding with our analysis and running it. And let's go ahead and take a look. You can see under our estimates right here, our unstandardized estimates, and these are our standardized estimates. You'll notice that basically, all of these paths under our unstandardized estimates, these are the ones that we've fixed to 1 already. So there's nothing being estimated there. But then you've got the unstandardized factor loadings that are given right here and then also right here. So those are all our unstandardized factor loadings that are given. You can also see because we standardized our intrusions and avoidance variables, basically fixing both of those to 1, then this actually produces the correlation between those two latent variables. Everything else in the model, though, is in unstandardized metric, and you can see up here this is actually the covariance as opposed to the correlation because we didn't set the scale of these variables, these error terms, to 1. We didn't fix the variances to 1 there. So at any rate, let's go ahead and look under our view text and look at our output, and you can see in terms of the model fit, it actually turned out to be a very good fitting model. You can see that we have our chi-square goodness of fit test, and you can see it's non-significant. That's certainly an indicator of good fit. We have our GFI and AGFI are very high, 0.99 and 0.98. I discussed that a little bit more in the PowerPoint in terms of conventional thresholds. TLI and CFI, both of those are indicating good fit. Those are well above 0.9. As we scroll down, you can see the RMSEA that's given. It's 0.017, certainly well below 0.05, which is an indication of close fit. And you can see the P-close test is non-significant. So all of those are indicating that we have a very nice fitting model here. If we go under estimates right here, and then we go under matrices, you'll see that where it's got implied correlations right there, you'll see that we've got the correlation, the model implied correlation between the avoidance factor and its associated phantom variable, and then also between the intrusions factor and its associated phantom variable right here. So you got 0.907 and 0.959. And so to obtain our reliability estimates, our values of omega, all we need to do is to square those two estimates. So I'll show you really quickly. We can just say 0.907. That's between the avoidance factor and the phantom variable right there. If I square it, I get 0.823 roughly. And if we do the same thing for the intrusions factor, if I take 0.959 and I square that, I get an estimate of around 0.919. Now I can also create my confidence interval estimates by going under, I still selected the correlations up here, but then going down to bootstrap confidence, and so now you can see that I've got my confidence interval that's given. So in this case right here, I can just, you can see, let me kind of scroll up a bit here, basically this matrix is associated with the lower bound for the confidence interval, and this is associated with the upper bound. So basically I can generate the lower bound estimates for the reliabilities for the two factors by squaring this value right here and this value right here to get the lower bound estimates, and then to get the upper bound estimates I can scroll a little bit further, and then I can just take the square of this value right here and this value right here. And so the values from an earlier run are included in the PowerPoint. Okay, so let's move on to our second approach using the User Defined Estimands. So the reason why I put this approach together is you can see that if we're using the phantom variable approach, things can become pretty cumbersome if you have a fairly large factor model. And so what I thought I would do is kind of show you how you could estimate omega using these estimands. So you can just kind of stick with the basic model that I showed you earlier that looked like this. So where we don't incorporate the phantom variables. But now to use the user-defined estimands, we do have to consider a couple of formulas for computing our omega value. So basically what I've done, what I'm showing you right here is just a screenshot of what I will show you shortly using AMOS. But basically right here what we have is the box for incorporating our user-defined estimands, and what I'm doing is I'm using these estimands right here to compute the values that are associated with these two formulas that are given right here. So the top one right here is going to be associated with the intrusions factor, so I'm computing that, and essentially in the numerator for the omega formula, what I have is a summation followed by lambda ij's. Basically sum up the items that are associated with factor j, and then square the sum of the factor loadings. These are the unstandardized factor loadings. So once again, basically sum the unstandardized factor loadings for those items that are associated with factor j and then square them. And then in the denominator, you'll see we have what we just computed in the numerator plus the sum of our measurement errors. Now the second formula is for the computation of omega for the avoidance factor, but because we have a covariance between two of our error terms, we need to account for that in the formula. So in this formula, you'll see that what we have in the numerator is exactly the same, and this portion of the denominator is the same as what we had above, but now we also are going to incorporate this element right here, and that is 2 times the sum of all of the covariances that are included in the model. And because there's only one covariance included in the model, it's just basically 2 times that covariance. Now for us to use the user-defined estimands with our model, what we need to do is to label the parameters that are in the model. So you'll see this is returning back to our original CFA model. You'll notice that again, we fixed the variances of both of these latent variables to 1, but then I've also incorporated labels for each of the elements that's incorporated into our formula. So you'll notice that we have to sum up the factor loadings. We have to get that. We also are going to have to sum up the error terms, and we also are going to have to incorporate the covariance, the sum of all the covariances in the computation. So what I did was I labeled each of the parameters that are required for computing our estimands. So really quickly, just if I right click on this arrow, go to object properties, you can see I've named this load 1. You can see I've named this load 2, load 3, load 4, load 5, all the way to load 8. The error terms, I've just named them error 1 all the way through error 8. And then I've also labeled this covariance here. I just labeled it cov 1. And the naming is arbitrary, but I just wanted to be pretty descriptive in how I set this up for you. Now once you've set up the basic model, then you will, at the very bottom of the screen, it may be a little bit hard to see right here, but it's down here, it says not estimating any user-defined estimand. So what I want to do is to specify the estimands, and so to do that, I'm going to click on that little area right down there and then go to defined new estimand. So I'll click on that button, and then this box was going to open up, and this is where I spelled out everything or typed in everything, all the code that I showed you just a second ago. So the first thing I'm going to do, and oftentimes I like to incorporate comments in my syntax, so I'm just going to type in an apostrophe and then follow it up with we have estimands for composite reliability, omega for intrusions factor, and you can see that that's all appearing in green. So when I run the analysis, AMOS is not going to really focus in or do anything with that information. So next I'm going to specify an estimand that captures the numerator of our formula. And remember that the numerator for our omega formula is the sum of the factor loadings for the items on a given factor and then squared. So I'm going to do this for the first factor. So the estimand that I'm going to create, I'm just going to call it NUM1 for numerator for the first factor here, and we'll say equals, and then I'm going to type in load 1 plus load 2 plus load 3 plus load 4, and those are the labels that are associated that are incorporated in the diagram. Next, I'm going to put this all in parenthesis, and then at the end I'm going to put a caret and then 2, and that's saying basically square the sum of those values that are inside our parenthesis. So that's for the numerator. Then for the denominator, I'll type in DEN1 and say equals to, and then for this, recall that we're basically taking the numerator that we just computed and then adding to that the sum of the errors. So in this case, I'll just say num1 plus, and then we'll say error 1 plus error 2 plus error 3 plus error 4. Again, those are the labels from our diagram right here, our drawing right here. And then for the last step, I will hit enter right here, and I will type in omega and 1 and equals, and then we'll just say num1 divided by DEN1 right there. And so that is the formula, that is the code that we need in order to generate the reliability estimate for the intrusions factor. And let's also do the same, or compute omega for our second factor, which is the avoidance factor. And so we're going to be using the labels for that as well. Okay, so now you can see that I've typed in all of this information. You can see I've incorporated right here. This is just a comment line again, and then we've got our computations that are given right here using the labels associated with the avoidance factor. And once again, you can see that I've added the 2 times and then the covariance label right there. If I happen to have more than a single covariance, then I would be multiplying 2 times the sum of the covariances that are being computed. So once this is all done, and again, this is our omega 2, and here I've just got numerator 2 divided by denominator 2 because those are the estimand names right here. Once I've set this up, then I'm going to go up here and click on check syntax. I'll click that, and you can see at the bottom now it says under description, it says syntax is okay. So if there were any errors in the syntax, it would show up down here. So at this point, what I need to do is to save this file containing our estimand. So I'm going to go to File and then Save As. And you can see I've typed in a file name right here. We'll just call it Final Estimands, and click on Save. I had already created it, so I'm going to save over it. And now I'll click out of this, and now at the bottom you can see where it says Estimating Final Estimand. So that's the name of that file that contains our estimands. So next, what we'll do is we will go under Analysis Properties again. And under our output, we can ask for our standardized estimates, squared multiple correlations, or whatever. We don't need to use the implied moments in this particular case because we're not using that phantom variable approach that I was talking about earlier. So I'm just going to stick with this, and we'll go under Bootstrap, and we'll also stick with the same selections that we had gone with before using our phantom variable approach. And so now when I click on Calculate Estimates, you can see we got our chi-square right here in our information. If we click this button right here, we have our unstandardized estimates that are given, as well as our standardized estimates. And basically the estimates are all exactly the same as what we had generated using that phantom variable approach. If we go under our text box right here and go to Model Fit, the fit is exactly the same as what we had before. You can see again, there's our non-significant chi-square test value. You can see our GFI, AGFI are the same as what they were before. TLI, CFI are the same. RMSEA down here is also the same. So basically it's the 0.017 that we found with the phantom variable approach. There's our P-close test. All that's exactly the same as what we had before. If we go under estimates right here, under scalars, you can see right here all of our factor loadings, the unstandardized factor loadings and the standardized factor loadings are all exactly the same. the covariances, correlations. All of this information is the same as what we generated before using the phantom variable approach. But if we click on the scalars and go down to where it says User Defined Estimands, we can click on that button right there, and so now we have our estimates that we had computed using our phantom variable approach, where we were taking the square of the model implied correlations between our phantom variable and our factors. You can see right here the omega 1 that was generated for our first factor, the intrusions factor, and omega 2, which was associated with our avoidance factor, and those values are exactly the same as what we had computed before. And we can also go to bootstrap confidence right here, and we can get the confidence intervals that we requested. So there's our these are our original estimates, and then you can see right here we've got the lower and the upper bound for the confidence intervals for those reliability coefficients. So that pretty well concludes this walkthrough. Again, the reason why I really showed you both of these approaches is because the phantom variable approach is fairly easy to use, but I can envision a situation where you might have a number of factors that are incorporated and you want to generate reliability estimates for those, and using those phantom variable approaches can become really cumbersome if you're trying to draw out these different models. So the user defined estimands seem like a reasonable workaround for you to be able to get the reliability information without having to draw out all those phantom variables. Okay, so that concludes this demonstration, and I appreciate you watching.